Dr. Ehrlich, welcome to the Tick Bootcamp podcast.
Thanks for having me.
We're really excited to have you and really excited to be here at the ILADS conference. So talk to us about first why you're here at ILADS.
So I'm actually president of ILADS, which is a sister organization to ILADS. ILADS is the professional society, and ILADS is the sister education and research foundation society. And every year, we have our annual meeting, and the day before our annual meeting, we have a joint board meeting of the two boards, and so, that's why I'm here.
I'm really excited to have royalty here. I noticed that you were on the board of directors, so that's really nice of you to take some time out to share first about ILADS, and then a little bit about what's going on in your world and your research project. So first, give us some information about your background. Where did you go to school, and what was your focus prior to beginning your research roles?
So I went to a small school called Alfred University in upstate New York. I was an undergraduate. I was a biology major, chemistry minor. And then after a couple false starts, I ended up getting my PhD at Syracuse University, actually studying human retroviruses. My mentor there, Bernie Poyce, was the guy who discovered the first human retrovirus, HTLV1, and he set the stage for the discovery of AIDS, or the HIV. And so I was in his lab when the AIDS epidemic started in 1981.
That's really cool. So talk to us now about the research that you've done in the past. We're going to bring you up to the present, but talk about the type of work that you did in the past and how that ultimately led to you doing work in the Lyme disease community.
So the way I ended up getting into the Lyme disease community is I was kind of drafted. In the early mid-90s, I was working on chronic infections, and specifically we were studying middle ear disease in children, which is the most common reason that children get antibiotics, the most common reason they see a physician, most common reason they get surgery when they have to put tubes in their ears. And there were two very different forms of middle ear disease. There was an acute form of the disease, and it was very clear to everybody that this was caused by bacteria, because you could culture bacteria from the ears, and if they had the acute form of the disease, you'd treat them with antibiotics and they would generally get better. There was a chronic form of the disease where the patients would be treated with antibiotics, they didn't get better, and they have fluid persisting in their ears for months, sometimes years. And so the feeling was that there was some sort of an inflammatory response to perhaps a previous infection, but it wasn't an active infection. And over the course of a few years, using new technologies, DNA-based technologies, we actually showed that, in fact, there were live bacteria in these chronically infected middle ears, but they had adopted what's called the biofilm mode of growth, where the bacteria actually form into a multicellular organism, okay? And when they form into this multicellular biofilm organism, they are metabolically, not genetically, resistant to antibiotics. And so that's why when you treat it with antibiotics, they didn't get better. And so because I had been involved in showing that other chronic infections were associated with biofilms, I was actually contacted by some of the Lyme people to see whether I thought that Lyme, might also, form biofilms, and that might, be, the reason why it's so difficult to eradicate. And so that's how I got into the field.
Oh, it's really cool. So, there are many folks who are focusing on biofilm as patients in the patient community. It's something that comes up a great deal, and there seems to be a lot of debate about whether or not the immune system has the capacity to break down biofilm or not, and when it does and when it doesn't. So let's walk back to your earlier research before you came into the Lyme community, and you said that you discovered that the bacteria were resistant to the antibiotic treatment, not genetically but metabolically. So can you give us some insight into that research that you did and how that now translates into the Lyme arena?
Yeah. So when I first got into the biofilm field, the people who'd created it was the whole concept was created by Dr. Bill Costerton. And he was a microbial ecologist, and he was studying how bacteria grow like in natural environments, like in streams and hot springs and that kind of thing. But they were the ones who had worked out that when the bacteria were in a biofilm, that they were resistant to antibiotics. And he thought that it was a penetration issue, that because they formed this matrix, that the antibiotics couldn't penetrate into the matrix. And I said, no. I said they could easily penetrate it. It's not that tight a matrix. And so we actually got our first NIH grant in this field. As part of it was to study that issue. And so working with Bill and his engineers, we showed that the antibiotics could penetrate into the biofilm matrix with no problem. And so that suggests that it really had to be metabolic. And so then we showed that you could take, if you could give the bacteria in the biofilm that were, we say metabolically quiescent, that is they're not dividing, they're not metabolizing much, if you were able to give them something that they could ferment, then they would become active again, and you could kill them with antibiotics in the biofilm. So then one of our colleagues a few years later, Pradeep Singh at the University of Washington, showed that there's actually this metabolic switch the bacteria have. It's called the stringent response. And he showed that if he knocked out the gene that's responsible for the stringent response in bacteria, they would form biofilms. But he could kill them with antibiotics just like they were, free-growing planktonic bacteria. And so that provided us now with a target for the development of true antibiofilm drugs. And so that's what my lab works on now.
Okay, so let's break that piece down because I can tell you that despite having interviewed many folks, both in the patient community, research community, and the clinical community, clinician community, that I'm not really clear about biofilms and what's happening in biofilms. So a biofilm is a response that's generated by the bacteria itself to protect it from what?
With the biofilm, so when the bacteria are in a biofilm, they're actually functioning as a multicellular organism.
Okay.
So
meaning there are other bacteria, viruses, and protozoa within, or only bacteria within the biofilm?
Both.
Okay.
So you can have what's called a single species biofilm,
okay,
where you just have a single species of bacteria. You can have a polyspecies bacterial biofilm where there are multiple species of bacteria. You can also have polykingdom biofilms, which include fungi and bacteria.
Okay, now, why would these microbes want to form this biofilm? How do they benefit from the biofilm?
Protection is the main thing, not just protection from if they're growing in a natural environment, protects them from predation, from being eaten.
By the
well. I was talking like in a natural environment, okay, not even like in a human being, because our biofilms are very ancient. Okay, so there's fossil evidence of biofilms going back over 3 billion years, and so it's a very ancient, protective mechanism. In fact, Bill Costerton, the founder of the field, as I mentioned earlier, had even postulated that the biofilm is actually the ancient form of bacteria.
Wow.
And that the planktonic form, which is what mostly we'd studied for the past 100 years, actually evolved as a way to colonize different sites. Just like if you have a coral reef,
yeah,
that the coral reef, that's kind of the main body, but you have these zoanthoi that go off periodically to colonize a new site, And so I think that's where Bill got that idea from. But the bacteria produce a matrix, and that's what defines the biofilm, is the production of this matrix. And you can think of it as very similar to the matrix that your bone cells produce. Okay, so your bones are alive. You've got cells in the bone, and they produce a matrix. Okay, and we know, that we always tell people, like, if you don't want to get osteoporosis or something like that, you need to exercise and lift weights, because putting stress on the bone, it strengthens, the matrix. Well, the bacteria do the same thing. If you put a shear force on a bacterial biofilm, it will make it more rigid. It will make it stronger. So it's literally, that's why I say it's literally a multicellular organism, that can respond, as a collective, against, any sort of an insult.
I absolutely need to have a long form podcast with you because this is fascinating and it's something that is really important in the Lyme community.
Sure.
Because there's a lot of debate about biofilm busters and whether they're necessary and or whether or not antibiotics can penetrate, whether or not the immune system can penetrate it. So I'd really love to build this out with you in more detail. But for the purposes of our limited time together today, can you talk to us about the work that you're now doing and how you believe the work that you're doing now will be helpful to folks in the Lyme community?
So one of the things that I want to make really clear to people is we don't currently have any true anti-biofilm drugs.
Okay.
People talk about biofilm busters, but from my perspective as like a bacterial physiologist, there is no biofilm buster out there that's commercially available at this point. There are some antibiotics which are more effective than others.
Passing through the matrix.
They all pass through the matrix.
Okay.
The question is, do they hit some function that the bacteria need that is active when the bacteria is in a biofilm? Because most antibiotics are going to hit some function that's not active, and so that's why they don't work.
Okay, so what's happening inside the biofilm is that there's a switch that goes off, and the microbe is not in a form that the antibiotic can kill. And what you need to do is not necessarily bust the biofilm, but you need to switch on the active form of the microbe so that the drugs can kill it.
You understand it precisely. I wish I could say it as clearly as you just said. That was very, very good. And so that's exactly what we're doing. So this switch, the name of the switch is called REL-A, okay? And what we have done in my laboratory is we have developed small molecule drugs which inhibit REL-A. And so if we treat a bacteria in a biofilm with our compound, okay, the idea is to repotentiate the biofilm against classical antibiotics. So we're saying what we're doing is we're developing a co-drug. And so if we treat, with our drug and an antibiotic, we can kill the bacteria in the biofilm, 3-4 logs better than the antibiotic by itself, And but I say like 3 or 4 logs, it was 1,000 to 10,000 times better,
That is awesome. I can't thank you enough, not just for taking time to share this with us, but for doing the work that you're doing. One of the reasons we wanted to come here to the ILADS conference is we want to thank folks who are making a career out of helping sick people in the Lyme community, and this has been a fascinating short period of time to spend together. So I do want to invite you back to a longer form podcast if you could take some time out to be interviewed by me and my co-host Matt Sabatello, because this is really a fascinating topic. So again, thank you for taking time to speak with us, and thank you for doing the great work you're doing.
I would love to do that. You just let me know when you want to do it.
Thank you very much. Thank you for coming on.
Thank you for having me.